So without further ado, Brian Koch with Michels Corporation. He is our third presenter. And Brian, the floor is yours.
Thank you very much, Gerald. My name is Brian Koch. I work for Michels Corporation. Michels is a family-owned and operated infrastructure and utility construction company. Foundations division is one of the 10 operating divisions. I'm going to be presenting on a case study of I-74 over the Mississippi River. The I-74 bridge is currently being constructed. Some recent construction milestones include the arch key section was set recently on the westbound bridge. The construction is being covered by webcam and social media. So as being part of the foundations, we're typically the first in, first out. So we don't see the progress of the structures being built. So this is a good new age way to keep up with the construction process. My goals for the presentation are communicate how the bidirectional load test can provide valuable information that can have a positive impact on the project's cost and schedule, and also provide a contractor's viewpoint on how to execute the construction process of the bidirectional load test. The project location, we're in the Quad Cities. On the Illinois side, it's Moline and Rock Island. Iowa side is Bettendorf and Davenport. The metro population of this area is about 400,000 people. It's kind of an industrial area on the Mississippi River. The existing structures, there are a pair of suspension bridges that are currently out there and being utilized. One of them was constructed in 1935, the other in 1961. At that location, the river is about 3,372 feet wide, and these pair of bridges were considered functionally obsolete. Right now, there's 2 narrow lanes going each direction, and the shoulders are minimal, so they're about 1 foot wide. During the bid phase, we reviewed the contract specification. This project included a bidirectional load test on a demonstration or a test shaft that won't be used as a production shaft. It also, one of the unique things that I thought on this project, there was a confirmation boring at the location of the test shaft. And also the plan notes indicated the bidirectional load test results may change the production drill shaft dimensions in a future plan revision. We had to take that into consideration when we were bidding the project. So once we have to do the bidirectional load test, we need to find a subcontractor that can perform the work. So that means we've got to reach out to the industry. There's specialty contractors that perform this work, and we get quotes from them. Then once we have that information, typically we pick a sub based on their cost, reputation, and past performance with them. Once we pick that subcontractor, they provide submittals that we turn into the owner. Submittals typically include the material procurement list, fabricated steel plates, angle iron, the load cell itself, and all the various strain gauges, hoses, telltales, and all the other components for performing the test. Once we're out there, we hired a local confirmation boring company. Prior to the installation of the test shaft, that company went out and had to take a boring at the specific spot. They sampled 10 feet below the bottom of shaft, or a minimum 30 feet into the bedrock. Out at that location, we were drilling into sandstone. And the boring company provided from that sample that they took the percent core recovery, the RQDs, and the unconfined compressive strength of that material sampled. Once we had that information, we submitted it to the engineer of record for review. Once the confirmation boring results were submitted, we started the mobilization process of manpower and equipment out to the project site to install the test shaft with bidirectional load test cell. For me, this was a unique job site. 233 of the 242 drilled shafts were installed off barges in the Mississippi River. You can see there's a photo of one of the drill rigs being loaded onto a barge to be pushed out and set up for that initial test shaft. The construction, the typical drilled shaft construction you'd have anywhere. We utilized permanent casing. We seeded it into the bedrock. We performed soil and rock excavation. As you can see in the photo, plenty of inspectors out there taking a look at what we were doing on our day-to-day operations. Then when we had the shaft excavated, we utilized the trimming method, wet method techniques for the shaft. And Paul was mentioning different techniques used to clean out the bottom of the shaft. We utilized airlifts out on this project. The rebar cage fabrication. So typically, rebar cages are tied horizontally off horses on the land. This is the same method we utilized out here. Then we loaded it onto a barge and transported it out to the platform that we were working off of. Once we had that taken care of, we installed the bidirectional load test cell. It was welded to the fabricated plates, both top and bottom. Then we had a tremie funnel welded to the plates as well to have the tremie go down through the rebar cage and fit through that hole that was cut into the top plate. Once that is all welded up, the cage is hoisted and set onto the bidirectional load test setup, and the top plate is then welded to the bottom of the rebar cage. Once that's taken place, the cage is hoisted and set inside the casing to the required elevation, and then you move into the concrete placement. Once the concrete's placed, it was required that we did non-destructive testing. On this project, they required CSL testing. Typically, you'd want to test shaft between 4 and 7 days of this size. And then on to performing the bidirectional load test. Typically, the day before you perform the test, the company comes out and gets the shaft ready. They attach all the survey instrumentation. They connect to the hoses, strain gauges, all that stuff is checked, so they know the next day they are ready to perform the test. This unique job site required installation of nearby pipe piles to mount survey equipment to, because we couldn't utilize the barges out there because they were always moving with the water level. So that was one item that we had to install uniquely to this project. It is a minimal testing, minimal amount of equipment to perform the testing. They bring out a few Pelican cases full of pumps and data logging equipment. And in my opinion, the test is very non-eventful. The drill shaft doesn't move much, and it doesn't move very quickly. So some of the inspectors that came out on the site, I think they were expecting, like a rocket ship taking off. It just definitely doesn't do that. The report results, once you get that data from the field, the subcontractor goes back and analyzes the results. And typically, what we had in our specifications, items included the load distributions, skin friction, end bearing, load movement for end bearing, upward shear. It also included some curves, the top load movement, side shear creep limit, end bearing creep limit. On this test, the plan originally assumed, the design plan originally assumed for piers 10 and 11, a nominal bearing resistance of 0, a nominal side resistance of about 2,700 kips, The bidirectional load test results for this project, the sustained upward side shear was about 2,500 kips, and the end bearing resistance was 6,000 kips. So the original design had 0 for the end bearing. The load test showed 6,000 kips, so a significant increase. The bidirectional load test report review. The engineer of record indicates the soils reacted better than assumed in the original design. The plan revision would be forthcoming for piers 10 and 11 to reduce the rock socket length for the project. So from the plan revision, our rock socket lengths were reduced by about 42% for pier 10 and 11. In the original plan, we had a 28-foot socket. Those sockets were reduced down to 14 feet or 20 feet on a few of the shafts. We reduced the rock socket quantities. Typically, our rock socket excavation cost is between $2,000 and $3,000 a cubic yard. So we did experience some cost savings with that shaft length reduction. I want to talk a little bit about the schedule. The bidirectional load test provided valuable information that can have a positive impact on the project's cost and schedule. Items to consider with the test are additional schedule to perform the test. We had the confirmation boring. That took about 12 days to perform the test, do the testing of the material, get the report out to the engineer. The test shaft construction, that takes about 3 days to install that drilled shaft out there. They were relatively short shafts, so it didn't take very long. GSL testing, typically, depending on cure time, it takes up to 10 days. I have done some tip testing in the past as well, and that reduces that time of the testing. So that's an option to reduce some of the time of the schedule there. And then the bidirectional load test takes probably 8 days to perform the test and generate the report. And then up to 14 days for the review of the load test report and then potential plan revision. So you're looking at about 40 days overall added to a schedule. This particular schedule, it was about 1.5 to 2 years long, so 40 days wasn't that big of an impact to this schedule. There are ways to mitigate those schedule impacts. Like Paul said earlier, if you perform the test program prior to actual construction, you can utilize that across the board. He did it on his project. I've also been a part of a project with Charles on the Zoo Interchange in Milwaukee. We did a test program as well prior to the job starting. So we were able to utilize that data to then go into design as well. Another thing we can do to mitigate that schedule is to allow the contractor to run concurrently once the test shaft is installed and that data is being reviewed. Allow the contractor to then go into production, and that'll give you concurrent operations that also has some schedule savings. So in conclusion, the bidirectional load test saved the I-74 Mississippi River Bridge project the following. Money, it reduced the rock socket length. Schedule, the time to construct the shorter drilled shafts obviously was a time saving. Natural resources, we didn't utilize the fuel or the concrete to produce the extended length drilled shafts. And I always say it saved the design team some loss of sleep knowing that the capacities used in the design were confirmed. So with that being said, thank you very much for inviting me to this, Gerald, and I'll pass the control back to you.
Thank you, sir. Thank you for a very interesting presentation that once again showed that the increased testing does save money.